getting cold, but it's feeling warm. Your lies are getting old, but I'm getting stronger. I'm getting stronger. 'Cause I'm fine on my own. So don't even bother to come back, 'cause I am done. I'm fine on my own. And boy, your pretty little lies are getting old. All those late nights I waited for you, they're gone 'cause we are through.
Hello, everyone. We are going to have the routing security SIG meeting. Okay. Hello. Good morning, everyone. I'm glad to be the forum acting chair here today. As we all notice, the RPK has been the center of inter-domain routing security for more than a decade, and the RPK is also the most important reason why we founded this SIG several years ago. And as we charter this SIG, both academic community and industry community are expected to contribute to share their impact. So today we are going to hear from them later in this forum, all about the RPKI. And after all the presentations, we'll open the floor for questions if we have time to spare. And all the speakers, please watch the time. Okay. And moving on to the agenda, I'm now handing over to Yash, who is the head of network operations at the New Zealand Research and Education Network. Today, she's going to talk about experience of RAN NZ with regard to routing security, especially with the RPK and the manners program. Yeah. So.
Here, everyone. I'm Yashaswini Ramesh. You can call me Yash, head of network operations at RIANS. While everybody seems to be going towards secure by default, I just wanted to say routing security has always been an integral part of RIANS, and I wanted to share the journey with you all. Who are we? We are New Zealand's NREN, that is National Research and Education Network. We are a purpose-built network for supporting our research and education sector. We are one amongst the 122 around the world, so I'm sure there are a lot of NRENs from Asia here. We have 100 gig backbones across the country. We are an anchor tenant on the Hawaii subsea cable connecting to the rest of the world. While we seem to be a small network, we have a pretty large footprint in terms of connections, IXs, and peering exchanges. Our members are all the 8 universities, CRIs, some independent research organizations, and some polytechnics. So what does my team do? We do end-to-end network operations. My team does architecture, design, testing, BAU, on-call, name it, everything is done by this team. Our optical infrastructure is provided by One New Zealand. We switched to them last year, but we manage the core routing infrastructure, and our routing security has always been an integral part of us. So how did it all start? RIANS, at the time it was called Karen, funnily, was started in 2006. Since we were a purpose-built network, right from its inception, we had handcrafted route filters put us in the memory edge. At the time, district here managing the routing infrastructure, so they put handcrafted routing filters on the memory edge. As RIANS really continued, some network generations started moving to RIANS. We had a team built, and the first thing was they did was to paste it into the base data. So I'm most happy to do it if you did all the information sense. That was around 2015. So centralized advertising information. The first thing we did centralizing it, as I said, giving the information of 3 points and MEM and IABAR and RIs, which was very simple. So we were kind of nudged to do this by our peer in Australia on it, because at the time they were providing certain services for us, and we thought this was the right thing to do. So we created automation for it. Now, once we have centralized member routing information, it was pretty much easy to automate route filters on member edge. And we had a really small team, and automation is the only way for us to operate efficiently, just because we are so small. After that, we've kind of had ideas, but never prioritized them with all the day-to-day operations till about when Manus came along. Manus came along and said they want to improve global routing security. They understood that no one person has a full view of the internet, so everybody should, be accountable for their part. And what their values and what they were thinking about aligned with our own thoughts, and so we jumped on board with it. And it also formalized what we were already doing and gave us new approaches that we could improve ourselves. So we were on board. So in 2020, Rians became the first network operator to join Manus in 2020. And sadly, unfortunately, we are still the only network operator in New Zealand that is Manus compliant, which we don't want to be. We want, we want New Zealand to be fully Manus compliant, all network operators. So if any New Zealand network operators here, come talk to us. It's pretty easy. I think you are already doing some of it. Please jump on this. So who are Manus? They're a global initiative. It's not a standard body, but they're a group of passionate individuals who have joined together to make internet more secure. Luckily, with the Endrin community, we are lucky that a couple of our Endrin peers are part of the steering committee. So we encourage within the Endrin world as well. They understand it's a collective, it's a collective responsibility, and it's very, very collaborative. And they've developed really, really cool tools in the last few years, and it's made it very easy. It's also action driven. So depending on what kind of operator you are, you have certain actions to do. So I'll focus on network provider actions. There are 4 simple ones. Filtering, that is making sure your routing information is correct and that of your customers. Anti-spoofing, that is source address validation. Maintaining your routing information, as you've seen, APNIC does it pretty easily. You can create your ROAs and update it. And last thing is about making sure you're globally accessible. That is your whois and peering DB and all of those contacts are rightly set so that you're contactable. Why? Why did we jump on this? Of course, the reputation. You don't want your names, with a DDoS hijack or your one of your addresses participating in DDoS. Availability. These hijacks will remove their availability. You don't want your data to go to somebody else. So security. And lead by examples. The education R&D sector is always about leading by example. So to go towards our Manus journey, in 2019, we created Rian's own ROAS. And we also enabled route origin validation on the upstream edge. So that was enabled in 2019. And scarily, we enabled it just before Christmas, but that worked well. We came back and we had few more steps to do, just updating contacts, making sure a few more mandatory steps, and we did our Manus application. So Aaron here, if you know him, is sitting down there, and he applied for us, and we got Manus approved. We didn't stop there. Manus at the time had certain recommended actions, and we took that on board, and we've enabled route origin validation on the member edge in 2022. And that was not strictly needed when we had source address filtering already, but this makes sure that it's coming from the right AS. After that, we've been adding anti-spoofing on member edge. It's all completed now. We've enabled CADA spoofer. And so if you're on NZNOG, you'll see our emails if something goes wrong. But also there's a lot more automation done, and we have config audits. So if there is new peering point or a new configuration, we make sure it is all manners compliant. What else have we done? Apart from being secure ourselves, we have championed it. We've done 6+ manners in our PKI presentation, and it's all mostly done by Aaron, but this time I really couldn't ask him. We've not only advocated in conferences, but we have individually gone to our peer network operators because we have relationships with them. We also have been advocating this to our government agencies like NCSE and others that need to take this up. And we've rolled out something called Routing Integrity Assessment Tool. So this tool was developed by Internet2, who is our US NREN. That's the beauty about NRENs. We share and share good ideas. It was developed to improve routing security, and it goes beyond manners. So we repurposed it for our own members and to encourage good routing practices. But also the main thing we wanted was about ROA updates by our members, because some of our universities hold a really large piece of IP addresses. So we wanted to encourage them. So shout out to University of Otago. They jumped on board. They were our first trial, and ROA was not there at the time, and they were on board and they updated ROA. And so they are 100% compliant, and they're also encouraging other universities in New Zealand to do so. We've also been keeping an eye on what is happening around the world. The Dutch government has made all the government departments mandated to implement RPKI by end of 2024. We see our South Asian friends, especially Bangladesh, being leading in the way they have adopted RPKI and ROA. It's about 90% there. It's really good. And although I don't have a slide about it, yesterday I saw White House released some roadmap for routing security improvement, and it was all about manners and ROA and steps they are going to get their network operators to do. And NIST is going to take this seriously. So if you're not doing now, I think this is the time. Jump on board. This is just showing. This is from the APNIC portal, the ROA adoption, and as you can see, the South Asians are leading the way. We are better than Australia, but we are not there yet. So if you are a New Zealand operator, please consider doing your ROA updates. And we have seen ourselves in the last 18 months or so that 50% across we see a bigger adoption of RPKI. So what's next for us? We want to continue championing manners. So we'll keep giving this a go. We'll keep doing our presentation and encouraging everyone. And if you are an NREN here and want us to help out, just reach out to us. You know how to contact us. We'll help you out. Continue to improve our tooling and operations. We always look for automation and anything else that we can do. And we're also looking at ASPA, which is Autonomous System Provider Authorization. While ROA is about are you authorized to announce the prefix, ASPA is looking at is this ASN allowed to propagate the route. That's a next step. We are part of a routing working group, ASPA working group from within the NREN community, and we're actively looking at what that means for us. What's been our learning? This is a journey, not a destination. While we have all the 4 ticks, manners can change it, change an action, introduce something new, and then we have to work on it. Automate. We do that a lot just because we are such a small team. There is no other way to keep up with this, and give your time, team's time. As a manager, that's all I can ask for. Prioritize this. This is important, and give them time to implement. I'm sure a lot of you do some of these steps, and it's just a matter of giving them some time and prioritizing it. Thank you.
Thanks, Yash. Our next speaker is Shuhe Wang from Zhongguancun Laboratory in Beijing, which is Computer Science Institute in China. His presentation today is going to touch upon the operational issue with inconsistent RPK data. So welcome, Shuhe.
No, so okay, I'm not used to this. Okay, so hello everyone. My name is Shuhe Wang. I'm representing Beijing Zhongguancun Laboratory and Tsinghua University to make this representation. Today, I'm going to talk about a problem in RPK deployment, which is caused by BGP's distributed nature. And the problem will still exist even if each ROA is issued correctly, precisely, and timely. That is the inconsistency issue between the looseness of ROAs and VRPs, while the latters are exactly generated from the former. How do I use this? Okay. Oh, okay. Thank you. Okay, so to begin with, let's first take a short review of the related knowledge of BGP security. One of the biggest vulnerabilities of BGP is route hijacking. The core reason is there are no restrictions on who has the right to claim the ownership of a prefix. So an evil AS could announce a prefix it doesn't have and divert the traffic from the right AS to itself, just like the ASB hijacking prefix P from ASD in this example of the page. To solve the problem, RPK is proposed to validate the prefix arrange matching. And under this structure, the prefix owner will first issue a ROA that describes the prefix arrange matching to the RPK repositories. Then, in every other AS, the relying party can download ROAs from the RPK repositories and generate validated ROA payload, abbreviated as VRPs, from the downloaded ROAs. Finally, those VRPs are sent to border routers within each AS, and the routers will execute ROV with the VRPs. Since VRPs are directly generated from ROAs, can we say a ROA and its generated VRP are always in the same condition of security? The answer is no. VRPs may additionally face more security issues when they are loose. To explain the reason, let's first look into the first question. What is the looseness of ROAs and VRPs? Before the discussion, we should notice that the ROAs and VRPs discussed here are all active, which means neither they or part of them are expired or revoked. Otherwise, they may have other security issues, and which is already addressed in other works. So previous work has already raised the concept of loose for ROA, which means not all subprefixes of the maximum length allowed by the ROA are advertised in BGP. The left example in this page has a non-loose ROA because prefix B and prefix C are both covered by this ROA. But we notice that even if the above condition is not satisfied, as long as for any address covered by the ROA, there always exists an advertised route that satisfies the following restrictions. Number one, the prefix can cover the address. Number two, the route is validated as valid. Number three, its prefix length is equal or longer than the ROA's max length. And number four, the route has the longest prefix length among all advertised routes covering the address, such as the second example in this page. Then it can also be regarded the same as a non-loose ROA. This is because as long as all the restrictions are followed, traffic visiting any address covered by the ROA is guaranteed to choose a valid route. So we just renew the definition of loose ROA here. So what may happen if a ROA is loose? It will mainly face two vulnerabilities. The first one is superprefix hijack. Let's look at the example of the page. If an attack route with the same arrange AS and the prefix of /21 is announced, it will be validated as not found. This route is not filtered because the prefix length is shorter than the route's prefix length range, and it is the only advertised route for addresses within the range of prefix C. So traffic visiting addresses within prefix C will follow the attack route and gets hijacked. Another vulnerability is forged range hijack, in which the attacker forges a fake route whose arrange AS is true and does not violate ROA, but the route's AS path is fake. So the attacker's AS is contained in the fake AS path. And in this example of the page, since the attack route has shorter AS path and is still validated as valid, it will be selected as a better route for prefix C. So the traffic to addresses covered by prefix C will follow the attack route, flows into the attacker's AS, the AS666, and gets hijacked. Since VRPs are directly generated from ROAs, we can apply the similar definitions from loose ROAs to loose VRPs. And the only difference here is to change the restriction of the route should be advertised in loose ROAs to the route should be in the router's local RIB in VRPs. And this is because for ROAs, it is used across the global network, and as long as the route is advertised, it is in the global network. But VRPs are used separately in each AS in a local vision of routes. So only those routes visible to the local router will determine the looseness of VRPs. So naturally, the next question is, do a ROA and its generating VRPs have consistent looseness? This is an important question because in theory, the arranged AS can only control how it issues the ROAs of its own prefixes to make them consistent with the routes it advertises. But the arranged AS cannot control if other ASs are still able to receive the exact routes it advertises. Well, sadly, the answer is no, because an originally announced route may not be able to advertise to another observer AS. To investigate the degree of inconsistency of looseness of ROAs and VRPs, we make an observation of route visibility across the road. We use 27 route views vintage points across all 5 RIRs, and we additionally use the CERNET VP in Beijing to supply more statistics from China. All these VPs are feasible, which means the VPs can collect most of IPv4 routes that are currently advertised in the global network. For better description, we define the prefix arranged matching in a route as fully visible matching if it is visible to all VPs. Otherwise, it is called partially visible matching. And in this example of the page, only the matching from AS1 is visible at all 3 routers, so it is fully visible, and all other matchings are partially visible. We can see that if a partially visible matching exists, or in other words, the matching is not seen in some other VP, then the related VRP at this VP is likely to get loose. By observing and comparing received matchings on each VP, we find that the number of total matchings as well as partially visible matchings varies greatly across different VPs. This means each VP will not be able to receive quite a few routes, and this will cause a large percentage of VRPs on each VP to be loose. We can see from the graph that around 36% of VRPs are loose on each VP, while the percentage of loose ROA is only below 10%. And such a huge gap in percentage shows that the inconsistency issue can affect a large percentage of prefix arranged matching, so this issue cannot simply be neglected. And besides, compared with fully visible matching, the ratio of ROV invalid matchings is much higher than in partially visible matchings. This suggests that besides hijacking and misconfigurations, the inconsistent visibilities of routes could also be a great factor to contribute to current ROV invalid routes. Since partially visible matchings could influence the looseness of VRPs, we further study their features and make classification of them. And there could be generally 2 categories. One type of matching is in those ASs where the matching is invisible, there is no other matching that can overlap with this matching in prefix, and we describe such matching as unilaterally visible. The other type of matching is in those ASs where the matching is invisible, you can still see another matching that can overlap with this matching in prefixes, and we describe such matching as bilaterally visible. And for the latter, depending on how the pair of matching are different from each other, they could be further divided into 3 types, namely the same prefix but different arranged, we say DPSO in short, different prefixes but the same arranged, we say DPSO in short, and both different in prefixes and arranged, we say DPDO in short. Then we examine the number and ROV states of each type of partially visible matchings. First, we find that unilaterally visible matchings is more common than bilaterally visible matchings, and the number of DPDO pairs is relatively the least. And later, we will talk about the cost of formation for each type of partially visible matching. And such number of matchings can give us a reference on the degree of occurrence for each cause. And next, different distribution patterns of ROV states of each type also suggest that each of them may be formulated by a different cause. For example, in SPDO matching, the ratio of matching with valid AS number states is much more than in other types. and this suggests that insufficient ROA registration for most prefixes. And in DPSO matchings, the ratio of matchings with invalid length state is much more than in other states. And the ROV state of most DPSO pairs are a combination of a shorter valid prefix and a longer invalid length prefix, which suggests it could be a potential prefix deaggregation. And in DPDO matching, the ratio of matching with non-valid states, including not found and invalid, is much more than in other types, which suggests potential prefix aggregation. Also, the ROV states of most DPDO pairs only contain one valid state, which suggests that either the original matchings or the aggregating matching are register-based ROAs only. Therefore, by combining the classification and features of each type of partially visible matchings we just mentioned before, we can dig into the problem that why partially visible matching could emerge. For a general process for the formation of partially visible matching, the picture in this page illustrates the flow. For certain arranged AS, we assume it will just exactly issue ROAs for those active and advertised prefix only. So a ROA issued by this arrange is non-loose originally. However, when the route with the prefix spreads to some transit AS, certain BGP routing policies in this AS may manipulate this route by either drop the routes or change the route's prefix or its arrange AS or change them both and continue to spread the change route. If the route is dropped, VRPs at any other AS that doesn't receive the route will probably be loose. And even if the route is just changed but not dropped and arrives as some observer AS subsequently, VRPs in this AS may still be loose. The looseness of VRP mainly depends on the relationship between the prefix of the changed routes and the prefix range of the VRP. So therefore, we call such policies at a transit AS as policies with hidden danger, because these policies have caused trouble to ROV in an unexpected way. So what are possible types of policies that may manipulate the matching? The first and most straightforward type is explicit route filtering, such as import and export filtering, route black hole, route damping, etc. Since such policy directly assigns some prefixes to drop, it could contribute to unilaterally visible matching. And if a prefix with ROA issued is filtered explicitly, there will be no route covering this prefix, and it will be vulnerable to both super prefix hijack and forged ring hijack. Another interesting finding is that when certain policies are combined, they could also drop routes in an implicit way. For example, we assume there is a mouse prefix which is announced by different ASs separately, but only one of them has indeed issued ROA for the prefix. When both routes are advertised, they first arrive at an ROV disabled router, and the route selection policy on this router will only keep one route for each prefix. And since the route from ASB has shorter AS path, the route selection policy will just filter the valid route from ASA and keep the route from ASB. The route from ASB will keep on spreading until it arrives at an ROV-enabled router. Since the prefix is only issued with ROA of ASA, the ROV policy on this router will validate the route from ASB as invalid and also drop the route. Then there will be no route for any address covered by the prefix in other ASs, so it is also vulnerable to super prefix hijack and forged range hijack. And besides just the dropping matchings, routing policies could also be transforming the matching. And one direction of transformation is route deaggregation. While the arranged AS is unchanged, route deaggregation will suppress the original route and generate one or a few routes whose prefixes are the subprefixes of the original prefix. So this policy could generate DPSO matching pairs. And the effect of deaggregation is twofold. First, for any deaggregated prefix, if its length is longer than its matching VRP's max length, then it will be validated as invalid length and gets dropped. Then the deaggregation can be seen as failed. And if the deaggregated prefix is dropped, its covering addresses will also be vulnerable to super prefix hijack and forged range hijack. And the other inverse direction of transformation is route aggregation. This type of policy is able to generate both DPSO and DPDO matching pairs, because aggregation can happen in either local AS or a remote AS. The ROV state of the aggregated route could also be one of all possible states. And first of all, if the aggregated prefix is issued with ROA and the arrange AS is the same as the transit AS doing aggregation, then this is a valid route and nothing happens. But if the aggregated prefix is not issued with any ROA, then the aggregated ROA is validated as not found. Then any address covered by the aggregated prefix will be vulnerable to superprefix hijack and forged range hijack. And there's an additional notice that in superprefix hijack, since the aggregated prefix is still there, to make the superprefix hijack successful, it is additionally restricted that the prefix length of the attack route should be shorter than all the original prefixes, but shouldn't be shorter than the aggregated prefix. The aggregated route could also be validated as invalid if a ROA with another arrange AS is issued for the aggregated prefix. It will be validated as invalid arrange AS number. And if a ROA is issued for a superprefix of the aggregated prefix, it will be validated as the invalid length. In both conditions, the aggregated prefix will get filtered, and the route aggregation can also be seen as failed. So any addresses covered by the aggregated prefix may also face the forged range hijack and superprefix hijack. So my presentation today mainly focused on the problem statement of the inconsistency issue between the looseness of ROAs and VRPs. Solving this issue could be another substantial work, but to complete this whole problem discussion, I want also briefly give some of my thoughts on how to eliminate or at least relieve the problem. I think the core solution should focus on eliminating the vulnerabilities of loose VRP. For forced range hijack, there are already many recent studies to defend this attack, and their main idea is to combine the AS path feature of routes to address the vulnerability. For superprefix hijack and deaggregated and aggregated routes, but validated as invalid, there are also two categories of solutions. One is at the RPK level, is to add specific routing rules for certain prefix, is to add, delete, or modify local VRP at each observer AS separately. Another is at BGP level, is to add specific rule for certain prefixes. And for example, the ROV++ has proposed to make black hole announcement for routes that could initiate superprefix hijack. And all in all, how to design a systematic solution for all the vulnerabilities is our next focus. Okay, so to conclude, we have defined the looseness of ROAs and VRPs and explain why they are vulnerable to route hijacking, including superprefix hijack and forged range hijack. Then we prove by observations of global routes across different VPs that non-loose ROAs do not necessarily lead to non-loose VRPs because observer ASs may fail to receive partially visible matchings of prefixes and their arranged AS. Then we dig into the reason and find that different types of partially visible matchings may be caused by different routing policies with hidden danger in transit AS, including route filtering, route deaggregation, and route aggregation. And in the end, to address the inconsistent issue, a brief idea is to try to eliminate the vulnerabilities of loose VRPs. And that's all for my presentation. Thank you for listening, and you're welcome to raise questions and discuss with me.
Thank you, Shunfa. Okay, please, all the speakers, watch the time, okay? So our next speaker is Massimo from NTT. He is going to talk about the coexistence of RPKI and remotely triggered black hole filtering from the perspective of IXP operation.
So, hello, good morning, everybody. Well, actually, it's just surpassed midday, so good afternoon. My name is Massimo Candela. I'm a principal engineer at the global IP network of NTT, which now is actually NTT Data. And the global IP network is our transit provider. So we are a tier 1 provider. And what I do there, I work on the automation and monitoring of the network. And if time allows, I develop open source software and I do some research. And this is one of those. In particular, this is a research done with my co-authors from several organizations. I would like to highlight Joanna. She's the researcher, the student that helped us crunch the numbers that you see in this presentation. Also, Manners, because Manners supported the project with their ambassador program. So what are we talking today? Well, we are talking about DDoS and hijacks, and in particular about their mitigation techniques and how they coexist together. So, you know, a DDoS, basically a target server gets overwhelmed by requests in order that other users cannot access to it. While this happens, the network is also overwhelmed. And the network is the part that we care in this presentation. And BGP hijacks, well, traffic is rerouted towards a destination different than the original one for various purposes like censorship or just sniffing the traffic or a typo of the prefix that you are overlapping other address space. How often these attacks happen? Really often. So from a report in 2023, Cisco said 15.4 million DDoS attack that years, and you can see the blue bars constantly growing. Cloudflare record 201 million requests per second HTTP during a DDoS. Microsoft a few months ago, 3.4 terabits of DDoS attack. So we are talking about the DDoS attacks are growing in number and also in size. And similar for BGP hijacks. Whatever monitoring platform will tell you thousands of hijacks per month. And some of these, they make newspaper headlines. So how, the good news is there are mitigation techniques. There are several mitigation techniques. And today we will talk about the remotely triggered black hole or RTBH. And of course, for the hijack, we'll talk about the resource public key infrastructure. So briefly, the remotely triggered black hole means that if you are under DDoS attack, you can announce a BGP update with a specific community, which usually involves the number 666. And if and your peers, when they receive this BGP update, if they accept the announcement, they will start rejecting. They will start actually not sending you any more traffic. And what is the goal? The goal is not to save the service. The goal is to reduce the load on the network. So the server, the web server or whatever, that is gone. You just want the traffic to stop toward that destination. And RPKI, I mean, you know how it works. You basically create a route origin authorization that says which prefixes your autonomous system announces, and other peers that they are doing, other ASs that they are doing route origin validation, they can use this publicly verifiable association between prefixes and AS to decide if they want to reject or accept that specific announcement. So when I say that this is for dropping the traffic, so RTBH is actually for dropping the traffic, and you just drop it all for that specific target. But there is also a more sophisticated, slightly more sophisticated way. So your, I don't know, for example, your upstream provider, in this case, this is our NTT. They can offer you some additional communities. They do something a bit more specific that is called selective blackcalling. So if you would, for example, use this 664 community, you could say something like, oh, drop all traffic that is coming from outside of the country. So like if you operate service in Japan, you can say, drop all the traffic that is out of Japan. And in that way, you may be able to still cater for most of your customer while drastically reducing the amount of traffic. This has nothing to do, or really few to do, with other techniques for DDoS mitigation, which we also offer, like, for example, scrubbing, rerouting, and all this alerting related, which are mostly related to cleaning the data. RTBH instead is just about dropping it. What is the problem? The problem is that a request for blackcalling can be RPKI invalid, and so can be dropped by other peers and not respected. Let's do some assumptions. The first assumption is that most of the blackhawling requests are probably going to be single IP addresses, so /32/128. And they are going to don't have a ROA covering them. And if a ROA is covering them, is about a less specific prefix, so they are going to be RPKI invalid. And you may say, well, I can create a ROA. I'm under attack. I create a ROA, then I do a propagation, then I do a blackhawling request. Well, the time doesn't go in your favor because it's well known that RPKI is actually slow. I did several presentations about this topic. You can find 2 here, and you can also find this paper done by a different research group, which really characterize the problem. So before you create the ROA is public, and other peers are going to fetch it, and you don't know when. A good amount of time goes by. So it's not fast enough for DDoS mitigation. How does it work, RTBH at an IXP? It works more or less like this. 99% of the IXPs, they do this. Some really few IXPs, they do something slightly more advanced where it require less cooperation from the peers, but essentially it's like this. You have a server which is under attack. You can craft a BGP community with a prefix that involves the IP of the server, and then you propagate it to the route server. In this case, they're all peering at the route server. Then the route server sees this community, like the 666 community, adds a specific next stop. This next stop is the black hole. This next stop is a IP that is going to be filtered out by ACL or assigned to a null interface. And then adds a community, no export, no propagate, and it's not advertised, and it's going to be propagated to the other peers. The other peers now, they can decide if they accept it or not. If they accept it, they will start to essentially drop the traffic, and you will not receive so much DDoS traffic. How can we characterize this? How can we put some number? First of all, let's look for data. We use the packet clearinghouse BGP collection. They peer a lot of IXP, so perfect. And we use the RPKI historical data from RIPE. The first thing we do is we go and we look for the IXPs on their website if they allow for blackcalling, if they support it, and if they do, what community and what next stop, whatever they want us to do to create this blackcall request. Then we take this information and we filter the data, the BGP data, to look for blackcall requests in 1 year span. And we find more than 12,000 prefixes blackcalled by 225 peers across 24 IXPs. And we answer the first question. Yes, most of the blackhole prefixes, more than 90%, they are single IP addresses, /32/128. But how long are these black holes? The majority of it, less than 1 hour to a couple of hours, so quite short. Some, they reach 1 day. Really rarely they go above, and there are some that they reach even more than 80 hours. How many times the same prefix get blackholed in 1 year? 50% only once. The other 50% between 2 times and 10 times across the entire year. And this is for the blackholing. Now let's look at the RPKI data. If we take all the RPKI data of the entire internet, and we try to analyze what is the strategy of creating ROAs at the moment. What we want to, so when you create a ROA, you put a prefix, which has a prefix length, but you can also put a max length. And when you put a max length, the idea is that you want to make the ROA valid for, I don't know, from this /24 up to the /28 or something like this. This practice is actually discouraged because it gives you, I mean, left you vulnerable to certain types of hijacks. And we try to see what happens in the data, and we do this heat map where y-axis is prefix length and x-axis is the max length. what we expect to see is this diagonal where essentially max length equals prefix length, which is the best practice. And we see a lot of it, indeed, more than 80%. That's good. But we also see a lot of this color squared here, which means that some operators, they actually use ROAS and they create them with this loose with max length. And if we focus on this last column where max length is 32, we see that a lot are coming from actually /24, /22, and 23 prefixes, so loose ROAS. But let's look at the data from the peers that they are doing this blackcalling request. Do they also do these things? Can this data overlap? Yes, indeed, if we look at the max length 32, the majority of the ROAS are coming from prefixes that they are /22, 23, and 24. Let's now try to combine this data set. Blackcalling with RPKI. And how do we do that? We create three categories. The first is RPKI strict. The RPKI strict are the users that they create ROAS for the black hole that they are doing. So the black hole prefixes has its own ROA. RPKI loose, the black hole prefix is covered by a ROA, but is one of those loose ROA with a larger max length. And the RTBH agnostic is basically an operator that doesn't care about RPKI while it's under the DOS. And it just does the announcement of the community, and the prefix is going to be RPKI invalid. And we see that the majority of the operators, they actually do exactly this. So while under attack, they propagate the blackcalling request, and they hope for the other peers or for the IXP to actually accept it and maybe do exceptions to the route origin validation. The RPKI strict is actually only 4. Despite being the suggested practice at the moment, this means that probably we should do better practice, something that is more scalable and doable for the operator. But at the moment, most of them, they do, they just don't care about RPKI while they are under the DOS. I understand that. So how often does it happen? Well, 91% of the IXPs that they do blackcalling, they actually do also RPKI. It's like if there is a subset of operators that they are knowledgeable about these techniques and they use it. So it's quite common. And 85% of the operators sent indeed RPKI invalid blackcalling requests. So if we analyze what they try to blackcall, this /32 are single /32, or they are like across different /24. So multiple /32 at the same time. What do they do? Well, a third of these prefixes are single /32 that they are just isolated. The remaining many are pairs of /32, so pair of IP addresses in the same /24. So the operator blackcalls 2 IPs of the same /24 at a time. This happens quite often, and there are a few cases where operators blackcall more than 100 to almost entire /24 by doing single IP addresses. Would be interested to investigate this practice. So what did we do here? We knew that there was this problem between a blackcalling request and RPKI. We wanted to characterize it. We wanted to put some numbers, do some statistics about it, and see how often this happened. And that's what we did. And in summary, 10% of the IXP members do blackcalling. Most of the blackcalled prefixes are essentially single IP addresses blackcalled for short time periods. 20% of the operators deploy RPKI, but they use loose ROA, and so they remain vulnerable to, potentially vulnerable to hijacks. 91 of the operators that they do blackcall, they also deploy RPKI, so this coexistence, this difficult coexistence is quite common, and 85% of the operators sent RPKI invalid requests for doing blackcalling. So they basically, they were trusting the IXP doing an exception to the route origin validation, which happens quite often, especially the one that they have route service with Bird, but also other ISPs to accept this request, which actually happens much less often. So this is the conclusion, and this is my contact. Thank you very much for your attention. And if you have questions later or if there is time. Thank you very much.
Thank you. Thank you. In addition to my main job, I'm also a consultant to an IXP in China. I think Massimo's presence today here in this forum is going to help me a lot. So our next speaker is Professor Liu from Tsinghua University. Today, he is going to propose a new type of RPK assigned object, which enables multiple autonomous systems to collaboratively and securely to announce IP prefixes.
All right, folks, nice to see you again. Today, I'm very happy to present our work recently to propose a side group of multiple origin analysis for use in RPKI. So this work is mainly done by the leading author, Li Qi, but she is not be able to travel here, so I present on her behalf. So let's say some of the very well-known introductions, like the RFC 1930 says that one prefix, one aliases. But in reality, the problem is there are the prevalence of multiple origin aliases, which is we call MOS. It's very common in the internet, probably by a lot of reasons like DDoS mitigation, business relationships, and other stuff like that. And distinguish between prefix hijacking and legitimate MOS can be very complex. So we do some measurement according to the current data of the internet. The things look like, let's see the highlighted text. So over 700 conflicts were classified as invalid by RPKI RV. But in reality, if we look at the sort of like the monitors, the only basically seeing about like tens of the attacks were really from the monitoring systems, tens of the hijacking events happen every day. So there is like a very like 10 to 90 times difference between the RPKI invalid versus the attacks. So there's a strong reason we believe that there is some false positives. That's actually our motivation why we think we should fix this stuff. So we are seeing some incompatibility between the RV versus the sort of like the actual monitoring stuff, the MOS basically. From all the measurement, we see some cases. They are real cases. They are what we see from our measurement result, and we take them and present here. So, for instance, the most one of the most prevailing cases are the multiple ASs from the same organization. They announce the same prefix. I don't know why, but this is a fact. I'm not know the reason behind why the multiple AS from the same organization announce the same prefix, but that's what happened in the current internet. So in this case, all three ASs announced the prefix P, but this prefix P is authorized to be announced only from this ASs according to the RV. So that's the easy conflict we're seeing here. Okay, this prefix is only authorized to be announced by this AS, but actually in the current internet, 3 ASs were able to announce this prefix. I think this is the same. This is the same thing. They are two different occurrence of the same case. And there is another case. There's some commercial partnerships between multiple ASs. Either they are a customer provider or they are peer. Basically, this AS we are seeing from ROA. This AS is only authorized to announce this prefix, but actually this AS is also announcing this prefix. They probably have some form of interesting commercial relationships, but this is what happened in the real internet. I think the problem here is we notice that in reality in the internet, because of the complex, maybe operational reasons, maybe business reasons, multiple ASs were actually for announcing the same prefix, which is only authorized to be announced by someone, which we know this is called mouse. But this is in contradictory with the RA design, right? RA design basically saying, okay, only one AS should be able to announce this prefix. So there is a conflict. The problems, how can we solve it? There were some potential solutions we think about that. First is like each collaborator can ask for an actual RA from the prefix owner. So can you also ask the prefix ASB, for instance, can also ask, can you give me this? Okay. The prefix fee also asks for the prefix owner. Okay, can you also give me an ROA for your prefix? I think this is a very ad hoc solution, right? You think about this. So the collaboration might be very short period, and it's very temporary, and overhead is large, and you have to ask the prefix owner. The prefix owner may also maybe understand, okay, why do you ask me for this stuff? Because I already authorized the ASA to announce my prefix. Why? So I think there's a lot of the non-technical negotiation behind this thing if we adopt this solution. Another solution is, okay, the ASA which is authorized to announce the prefix. ASA can, sort of like apply a RA on behalf of the other ASs. So ASA saying, okay, I might ask ASB to announce this prefix, so I can apply an ASA RA on behalf of the ASB without ASB's confirmation. The problem here is, what if the ASA is someone who is malicious? He might be sort of like asking for the prefix, asking for RA for other ASs without their contention. There could be some consideration here. If an ASA is abused its ability, it will cause problems, right? Another solution is like currently in the IETF there is something called the signed prefix list, which is saying, okay, each AS should sign something to prove or to certify, okay, that's all the prefixes this AS want to announce. The problem is that this is not solve this problem, because if we are seeing the problem is the signed prefix list has to be it works only if the RA/RV is valid. But the problem we are talking about today is the RA/RV is not valid. So today, to solve this problem in a more technical way, it's more concise, more technical, and more false proof way. We propose something called side mask group, or SMG. So the high level idea is actually quite simple. So what do we do? The SMG is basically asserts that in a group of ASs intended to collaboratively announce an IP prefix. So this group of people, they sit down together and they agree upon with each other, okay, we are as a group will be announcing this prefix. The procedure, let's go look at the procedure of this stuff. And the procedure of this stuff is actually simple. Or what we do is like the ASA who is authorized to announce this prefix by the RA, it will start to initiate this process. So he calls ASB and ASA or send an email or stuff like that. Okay, hey folks, let's together to sign an SMG object to telling the world that we are as a group will announce this prefix. So the process here is very straightforward. So the ASA initiates the side group object, and the ASA then set the SMG group to other members B and C, and each members B and C, after he agree, okay, I will be part of this group, will also sign this object by its private key. Then the ASA will verify all the signatures and aggregate all the signatures in a global signature. This global signature is a representation of a agreed appointment on this stuff. Okay, we three together agreed to announce this prefix. And the prefix owner can sort of like verify this SMG before add to the RPK repositories. This is a very simple SMG object we implement. We use in the signed object template for the RPKI in RFC 6488. Basically, it has the versions and it has the groups and it has the prefix. So it's a very straightforward, very self-explanatory object there. And for this stuff, for the SMG validation, there are two space. The state space of the SMG validation here has three states. The first state is the signature is verification is true, which means everybody's signature is correct. And second, if the consistency check is true, then the state of the SMG is valid. Otherwise, it's either suspicious or it is invalid. So now let's see the most important part, I think, how the SMG RV interacts with the RA RV. So first of all, the SMG RV only works in this space. So if the RA RV is valid or not found, then you can basically ignore the SMG. The SMG only works for if the RA and RV are invalid. So in this case, if the RA-RV is invalid, but the SMG RV is valid, then we can think this route is eligible. This is actually the key reason we propose this SMG. But if the RA-RV is invalid, but the SMG RV is suspicious, and we recommend eligible. This is consistent with the assigned prefix recommendation. And if the SMG RV is invalid, then the whole stuff is ineligible. But in the case when RA RV is valid, then SMG is basically irrelevant. So you can just ignore SMG. Or if the RV is not found, it's also not relevant anymore. And we do some operational considerations here, and there are some like the signature overhead, AS number sorting, and multiple valid SMG with the same IP prefix. For time of sake, I will skip this stuff. All the slides are open, so everybody can take a look at afterwards. And we do some implementation using the Octo RPKI. So basically, it's showing like this stuff is very with very small overhead. And we can basically generate the SMG in a very short period of time. It's compared to the whole RPKI time latency. This stuff is really negligible. And also feel free to check out our implementation open source on GitHub. And to conclude, so we are basically seeing from our measurement there is a conflict between MOS and RV architecture. So how can we solve this problem in a more technical way? There are a bunch of other ways we can solve this problem, like what I mentioned. We can call each other to basically help me set up this stuff. But I think all this stuff are not existing approaches are not very technical. And by generating a new SMG object in the RPKI repository, we can solve this problem in a more systematic way and more secure way. So the SMG allows multiple AS to announce an AS prefix collaboratively and securely, and supporting various business relationships, including traffic engineering, DDoS mitigation stuff. So regardless for what reason, we can solve this problem. And we do have a prototype in Golang and release all the stuff there. And also we publish stuff as the information draft on IETF. So feel free to check that. And thank you for your time.
Thank you, Zhutang. Thank you. Our next speaker is Dave from APLeague. He's going to share the overview of RPK deployment across 56 columns in Asia Pacific region.
Thanks, Tina. So 35 slides in 12 minutes. This is going to be fun. So who am I? Was a network infrastructure engineer for a long time. Now I'm a trainer at APNIC, and I look at lots of numbers. Got a couple of kids, few cats, and I like memes. So what are we going to look at? I'm going to talk about all the numbers. So we've looked at solutions, we've looked at how things can change, but we need to really look at what's actually going wrong at the moment. So we'll start with rower coverage. We look at this wonderful map that was shown earlier. As you can see, green is good, red is bad, everything else in between, we're somewhere there. Yes, New Zealand is marginally better. I will come to that. So globally, we're sitting at around 47% signed, almost 50%. We're getting there. Asia is doing very well as most of the continents. Africa is still a long way behind. North America is a long way behind, but that's because of their address space structure at the moment. So that needs to get fixed at some point. Within Asia, we have 3 sub-regions. So we have South Asia, East Asia, and also Southeast Asia. Lovely map colors again. As was alluded earlier, South Asia is doing quite well. Their numbers are fantastic. They've adopted this at great length with a lot of effort from the local community. So if we jump through these numbers, obviously I've sorted them best to not so best. Now I've added a new column this year. I've added the column POT means percentage of total address space. So it gives you a relative size of how many networks there are, how much address space is in each of these economies. So up the top, Bhutan, very small chunk of the address space, but they're also 99.3% valid. Fantastic. We get into Pakistan, 96.7. If you go back 3 years ago, they were in the low teens. So that has been a huge effort from some of our team, our community trainers on the ground, to get those numbers up to where they are. India, they've got a very large chunk of address space and they're still in the 80s. So this can be done on scale. This is not just oh yes, small countries can do it because it's easy. Well, it's the big guys can do it as well. Jump into East Asia. Again, Mongolia, not a huge amount of address space, but they're up there. Again, good local community, did really great work and did a lot of implementation. We jump down, Taiwan also doing really well. But down the bottom of the list, China has been consistently low for some time, and Korea has done almost nothing. So again, look at the relative sizes of the address space. I've shown you that, if India with 1 billion people and a lot of network operators can do this, everybody can do this. Southeast Asia. So again, we've actually got consistently good results through Southeast Asia. There are a couple of bigger players within the market. One thing of note is Singapore, V4 invalid. When I went digging through that, there's a lot of /32s in here. So that's RTBH. Now, I thought, okay, it's RTBH. I've just caught it when it was happening. But some of these have been RTBH black holed for 2-3 years. You can't tell me the prefix is still being attacked. Once you've stopped the attack, turn off the RTBH. Jump down to Oceania. So we've got a lot of small economies in here, but we'll split it up into Australia, New Zealand, Melanesia, Micronesia, Polynesia. So all the country codes are there. ANZ, yes, we're doing okay. Melanesia's beating us, but that's fine. So New Zealand, you have 10.6% of the address space in this sub-region. So I would hope that everything is going well. Australia, we still have, even though the HRM project or the Historic Resource Project is completed, there's still a lot of those historical resource holders who have not signed their prefixes. So they need to jump on board and actually start doing that. The V4 invalids that are in Australia and NZ are predominantly transit access ASN partnerships. So they'll be announcing their aggregates from their transits, but they've also announcing sub-aggregates from their access ASNs, but they haven't signed them. So if you are doing that relationship, then make sure you're signing your access ASNs as well. Don't forget about them. The main thing it'll be causing is suboptimal routing. Things won't be routing the way you think they are because your upstreams are only taking your aggregate announcements. The sub-aggregates, we're dropping them. We don't care. Melanesia, quickly run through here. Again, not too bad. The islands are doing really well. Again, not huge amounts of address space, so it's fairly low effort for them to actually do it. We bounce into Micronesia. Again, good consistent numbers. Federated States of Micronesia. You've got, what? Not a hell of a lot of address space. It's not going to take long to sign it. Please do it. And Polynesia. This is a bit of a mixed story, this one. Some are doing really well with this. Others need some help. Don't forget, APNIC are there to help. If you want someone to help you with your ROA signing, please reach out to our help desk. Dropping invalids. Again, red is bad, green is good. There's a lot of red on this map. Australia, we're doing okay. Now, this is down to a few factors. A lot of our in-country tier ones drop invalids. A lot of our operators sit behind them. I can tell when PNG are using one provider over another based on their ROV state. I can tell when they flip-flop their transit links between Madang and Port Moresby. So invalid drop rates in Asia are really low. You know, South Asia, 11%. Yes, it's fantastic. You've got all these countries doing 90+% ROA, but you're doing no ROV. Now, some of this is down to CPE. There's a lot of MICROTIC. Tons of MICROTIC there and in Southeast Asia. Until sort of 7 dot releases in MICROTIC, you couldn't do ROV. And if you haven't got a big enough router, you can't take full tables, so you still can't do ROV. So you can't win. East Asia, yeah, the numbers are okay. They're not fantastic, but they're on par with global averages that we see. So Oceania is better, but it's from this thing that I call fortuitous validation. My upstream is validating, therefore I look like I'm validating, but I'm not. Default routes still exist. So if you are taking full tables and you've still got a default route, the invalid traffic is going to go out through the gateway of last resort anyway. So if you are taking full tables, get rid of your default route. You don't need it. So what do I need to do? Obviously, go into your RIR, NIR portal and sign your routes. The other big thing, and everybody here has talked about this, is over-signing. Make sure what you're announcing in BGP is signed and nothing more. If you have a 20 and you are announcing down to 14s, sure, use the max length, but make sure you are announcing every one of those all the way through. It's unlikely that you are, so just do what you're announcing. Typically, I advise that if you are going to go on a ROA signing mission, actually clean up your BGP announcements. South Asia, I'm not going to have a routing discussion, but you do deaggregate a lot for no good reason. So go and check external sources. Go and look at route views, Radar or Cloudflare, etc. There's plenty of good sources of routing data out there, and make sure that what is out there is what you're signing. ROV, if you have a full routing table, come and hang out and do some training with me, and I'll show you how to actually do route origin validation. Set up a validator and start dropping invalids. If you haven't got a full route table, partial routes, or taking a default route, contact your upstream and say, hey, have you thought about doing route origin validation? I know a guy who can help you with that. And that's all I have. I told you I'd get you back on time. All right, thank you very much.
Thank you, Dave. Okay, since we still have like more than 15 minutes to go, now I open the floor for questions. If anybody have questions for the speakers. Okay. If have you got no question right now, I'm still encourage you to initiate discussions in the mailing list. Okay. Oh, Dave. Okay.
I have a question. My name's Dave from APNIC, speaking in my own personal capacity. The discussion about mowers. Now, full disclosure, I've had some exchanges with the authors over email. I'm still unsure why the perception is there that this is actually a problem. I look at how I actually sign rowers for the address space. And I did mention to them that it's my routes, my prefixes, my rules. If I want them to originate from here, I will sign a rower attesting that. So for me, logically in my head, mowers just seems to be creating a bit more complexity around the process. Is that a fair point, or am I not reading into it enough? Up to the authors to discuss.
Okay. 知道, you can come here.
Yeah. First of all, thank you for your exchange over the email. So it's very good discussion. So I think I think we do the problem statement we hear here is how can we make the mouse more compatible with the RPKI? And I totally agree with that. If the author, like the prefix owner, is willing to take this stuff, saying, okay, I will try to authorize a ROA for each of the ASs that are potentially be able to authorize my prefix. I think that's a valid solution. But our understanding is, what if like the prefix owner is not willing to do so, either because of the overhead or stuff like that? Can we have something sort of like more, more third party, more combined with the RPKI infrastructure solution to solve that? I think that's our only, exploration is in this regard. But I'm very happy to seeing like your thoughts about this stuff. It's very, very, very interesting, actually. Yeah.
Okay. As I mentioned, if you would like to continue the discussion, you're welcome to initiate discussions in the main list, since we have a special main list for the routing security SIG. Okay. Okay. So that's call it a day. Thank you, everybody.